Alright, now we will continue on for some other techniques of evaluating limits. So, what do we have here? We have the following. We have seen so far, we have seen how we can evaluate limits by using direct substitution. Now, evaluating limits by direct substitution works for an infinite amount of functions out there. However, it becomes very difficult. It becomes more difficult to find the limit as x goes to a of f of x, when the limit exists, but the limit as x goes to a of f of x is not equal to f of a. And we hinted about this earlier in the semester when we first introduced limits. Now, there are two cases that are very typical that you may see. And they are the following. One is when f of a is defined but it's not equal to the limit as x goes to a f of x, and two, when the value is not defined at all. So we have these two cases. Alright, so let's try to illustrate this. Let's try to get an idea of how this looks. Okay, so we have something like this. Let's say it's the x-axis, this is the y-axis, we have the origin here. So let's say we have some function like this. Say this is y equals f of x. And here we have some discontinuity. Let's say that here's where a is, and instead of a being what we expect it to be, f of a is somewhere up here. So in this case, f of a is defined, but f of a here is not equal to the limit as x approaches x. Because if you notice, as the x values get closer and closer to a on the x-axis, on the y-axis the output values are getting closer and closer to this open hole here. But we know that the value of a at that particular point is up here, but the limit is going to be this open hole here. So here in this photo, in this graph, the limit as x goes to a of f of x is not equal to f of a. And the other situation that we may have will be for so let's say the value is not defined at all. So you may run into this one quite often. Okay, so this one, the limit as x goes to a of f of x exists, but f of a is undefined. And this could happen with rational functions. With rational functions, the limit can exist, but you may have uh, the value at which it exists be undefined for the function. So let's see a couple of examples of this. So for example, take the following limits. So let's evaluate the following limits. We have the limit as x goes to 2 of x squared minus 6x plus 8 divided by x squared minus 4. If we notice here, we have a rational function. And when we have a rational function, we know that we could simply plug in the values that we're limiting to and then try to solve. But if you notice in the denominator, if we were to plug in 2, we will have 2 squared minus 4, which equals 4 minus 4, which equals 0. And we cannot have 0 in the denominator. So this is not allowed. So we have a problem. So what can we do to mitigate this? Well, one of the techniques that you could do is to factor. So since we cannot solve this problem, by using direct substitution, we will factor, then cancel like terms. Okay, so if you notice here, the numerator can be factored and the denominator is the difference of two squares. So let's work this out. So the numerator we have x squared minus 6x plus 8. The denominator we have x squared minus 4. Now to factor the top, we need to find two numbers that multiply to give us 8 but add up to give us negative 6. And let's see, to figure this out, you have to look at the factors of 8. So right off the bat, I could see that 2 times 4 will give me 8, and if both of them are negative, negative 2 plus negative 4 is going to be a negative 6. So we have x minus 2 and x minus 4. And then in the denominator, we have the difference of two perfect squares. 4 is the same thing as 2 squared. And we know from college algebra and pre-calculus that when we have the difference of two perfect squares, we could factor as follows. We could do x plus 2 times x minus 2. Notice here now, I have some cancellation. If, so long as x is not equal to 2, so since x is not equal to 2, I'm allowed to actually do this cancellation. So I'm going to cancel x minus 2 with x minus 2, and I will be left with x minus 4 divided by x plus 2. And now, continue. Let me try to continue on this side. Zoom out a little bit. Now, since x squared minus 6x plus 8 over x squared minus 4 is equal to x minus 4 over x plus 2, and this is whenever x is not equal to 2, then these two functions, and I will share this in GeoGebra, these two functions have the same limit. They're actually almost identical. So now, instead of finding the limit for this complicated function on this side, I'm going to do it with this one, which is a little bit simpler. So we have, move down, so we have limit as x goes to 2 of x minus 4 over x plus 2. But now we have a linear function in the top and a linear in the bottom, so I could simply substitute in the 2. So we have negative 2 divided by 4, which is negative 1/2. So we have that the limit of, as x approaches 2, of the whole expression is simply equal to negative 1/2. So let me try to move up to another side. Let's see. I do not want to erase. Show some space. There we go. Okay, so let's do another example. How about the limit? Let me make this a bit thicker. And it crashed on me. Okay. So let's say we're dealing with the limit as x goes to 1 of the square root of x minus 1 divided by x minus 1. Now this is a more complicated limit than the previous one. Notice x minus 1 equals 0 when x equals 1, which means that direct substitution doesn't work because we will get 0 in the denominator. So direct substitution does not work. But something that you may try whenever you're in a situation like this and you see a radical expression anywhere, you could try to multiply by the conjugate. You could try to rationalize either the denominator or the numerator to see if you get something much that looks nicer to work with. So that's what I'm going to do. I'm going to multiply essentially by 1 by the conjugate of radical x minus 1, top and bottom. So it's going to be radical x minus 1 divided by x minus 1, and I'm going to multiply top and bottom by the conjugate, which is radical x plus 1 divided by radical x plus 1. Now, when we do this type of multiplication, when we multiply fractions, we multiply across, and these are binomials. So let's be a little bit careful in multiplying. I always suggest, introducing the parentheses so that you don't get confused. Now we're going to multiply first the numerator. We're going to leave the denominator the same because we're essentially trying to get rid of this x minus 1. If we could get rid of that x minus 1, then we will be golden. So we have radical x times radical x. That's x to the 1/2 times x to the 1/2. Then we have plus radical x, and then minus radical x, and then minus 1. And then the denominator stays x minus 1 and radical x plus 1. Well, when we have the same base, we add up the exponents, and 1/2 plus 1/2 is 1, so this is just x to the first power. Radical x minus radical x is 0, so we just get x minus 1 in the top, and in the denominator we still have an x minus 1 and a radical x plus 1. Now, so long as x minus 1 is not equal to 0, we could cancel. We could actually divide these things. So let's divide. If we cancel them out, I'm left with a 1 in the numerator and simply radical x plus 1 in the denominator. And now I can actually evaluate this limit. I can actually simply evaluate this part. Why? Because I just showed that radical x minus 1 over x minus 1 is the same as 1 over radical x plus 1. So instead of calculating the limit as x goes to 1 of this, I'm going to calculate the limit as x goes to 1 of this expression. So I will simply plug in the 1. So I have 1 divided by radical 1 plus 1. This is 1 over 1 plus 1, otherwise known as 1/2. So this is again a way of evaluating limits by using some techniques from algebra and pre-calculus that you should know by now. Okay? Now let's maybe do one more. So example, let's find the following limit. Find the limit of f of x equals x cubed minus 6x squared plus 8x over radical x minus 2, and we want to find the right-sided limit. So right-sided limit. So right-sided limit. So that's the limit as x goes to 2 from the right side of f of x. We want to find the left-sided limit, which is the limit as x goes to 2 from the left side of f of x. And then we want to say whether they exist or not. Okay, so let's first take a look at what we're dealing with. So f of x is x cubed minus 6x squared plus 8x divided by radical x minus 2. Now we here have a rational function, and in the denominator we have a radical function. So let's begin talking really quickly about the denominator. The denominator cannot be equal to 0, so that's number one. And the radical, the expression x minus 2, must be bigger than 0. Cannot be equal to 0. We cannot allow it to be equal to 0 because we're in the denominator, so it has to be strictly bigger than 0. And this is true whenever x is bigger than 2, meaning whenever x is to the right of 2. So that means that the domain of f, so this means the domain of f is x has to be bigger than 2. We cannot have any numbers less than 2 or negative, because then we'll be breaking our domain. So now, what does that mean? That means that the limit, so this implies that the limit as x goes to 2 from the left side of f of x does not exist, since our domain is all x's that are bigger than 2. So we cannot have any values on the left side. Now, since the limit as x goes to 2 from the left side does not exist, and for does not exist, I'm just going to be writing D and E from now on. Then, by a theorem we had last week, by theorem from lecture 3, the limit as x goes to 2 of f of x does not exist. Because remember, for the limit to exist, the left side limit and the right side limits must be equal. So if one of them does not exist, then they cannot possibly be equal to the other side, unless the other side also doesn't exist, in which case, again, the limit just doesn't exist. However, just because the overall limit doesn't exist, the two-sided limit doesn't exist, does not mean that we cannot find one of the sides, one of the limits from the sides. So from the left side we now know that it doesn't exist, but what about the right side? So let's explore the limit from the right side. So as x goes to 2 from the right side of f of x, what we have is limit as x goes to 2 from the right side of x cubed minus 6x squared plus 8x divided by the square root of x minus 2. Now, we could factor the numerator. So notice everything in the numerator has an x, so we could pull an x out, and we'll be left with x squared minus 6x plus 8. And in the denominator, we could rewrite that as x minus 2 to the power 1/2. And again, if you don't remember, recall, square root of x is the same thing as x to the 1/2 power. So that's where I get that. Now, what can we do? Well, we could again factor the numerator. So I have limit as x goes to 2 from the right side. Again, we did this one before, so two numbers that multiply to 8 and add up to -6 are x minus 2 and x minus 4. And this is divided by x minus 2 to the power 1/2. Now, I'm going to do this on the side, but if you have, let's say, a to the power 2 divided by a to the power 1, by rules of exponents, this is the same thing as a to the 2 minus 1, which is just a. Similarly, if I have a to the power 1 divided by a to the power 1/2, then this is going to be a to the 1 minus 1/2, which equals just a to the 1/2. So that's what's going to happen here. Instead of canceling these two things out, I cannot cancel them, they don't have the same power. What I will have is limit as x goes to 2 from the right side of x times x minus 4 times x minus 2 to the 1/2. And this is because of this rule right here. I just basically did, this has power 1, this has power 1/2. So x minus 2 to the 1 minus 1/2 is simply x minus 2 to the 1/2 power. But now notice that I don't have a fraction anymore. And if I don't have a fraction anymore, I don't have to worry about the denominator being equal to 0, which means that I can happily just do the plug-in method and plug in for 2. Technically, what's going on here, we are going to be applying the laws that we had earlier. So this is going to be limit as x goes to 2 of x times limit as x goes to 2 from the right side of x minus 4 times limit as x goes to 2 from the right side of x minus 2. And remember, because we have a power up here, we could take it out by rule number 7. So now what we have is, well, limit of x goes to 2 to the right side of x is simply just 2 by the theorem of limits of linear functions. Similarly, for this is going to be 2 minus 4, so that's minus 2. And here's going to be 2 minus 2, which is 0, to the 1/2 power. So we have here 2 times minus 2 times the square root of 0. Well, the square root of 0 is just 0, and 0 times everything is just going to be 0. So the limit here from the right side is 0. So limit as x goes to 2 to the right side of f of x is just 0. And that's all she wrote for that problem. So that is the end of the problem. Now, despite our success using direct substitution and some algebraic manipulations to find limits and using the limit laws, there are some limits for which these techniques and these ideas just simply do not work. Especially when investigating the slope of the tangent line of some graph, such as the exponential function. If you don't remember, the exponential function is y equals, let's say 2 to the x, or y equals e to the x, which look like this. You know, they increase very quickly. They have a horizontal asymptote, these are standard ones. They have a horizontal asymptote in the x-axis. So actually finding out what the slope of the line is at a particular point can be very difficult. You know, if you have a tangent, a secant line here, getting that secant line and estimating to get the tangent line is not easy. So let's explore this particular problem, and this will lead us to a theorem that's going to really help us out when evaluating functions like this. So let's talk about this example. So we're going to talk about the slope of a tangent line. To f of x equals 2 to the x, which is this right here. Now we're going to estimate we will estimate, much like we did in lecture 2, we'll estimate the slope of the tangent line. At the point 0, 1. Okay, so we're going to estimate it at this particular point, 0, 1. So that'll be up here. Okay, so if you recall from lecture 2, to find the slope of the tangent line, I said that we take the difference in y divided by the difference in x's. Now, what do we have to do? Well, I don't have a specific point for my second point. I need 2 points to do this, because it's y2 minus y1, if you recall, divided by x2 minus x1. And for this I need 2 points. I only have 1. So I'm actually going to get another point, and I'm going to get it straight from the function. What happens if I plug in x into the function? So if I plug in x into the function, my output is just going to be 2 to the x. That's by definition of what a function is. So this is going to be the coordinate that I'm going to use to actually find the tangent line. And this is very similar to the problem that we did with the slope of the tangent line, again on lecture 2. So now, by definition of the slope, I'm going to call this my y2, and this is going to be my x2, which by default will make the point 0, 1, my y1 and my x1. So what I'm going to have here is the following. I'm going to have that the slope of the secant line, so I'm going to denote it by the slope of secant line, is going to be equal to 2 to the x minus 1 divided by x minus 0, which is simply 2 to the x minus 1 over x. Now that we have this, we could let x approach 0. So we're going to use we will now use a table to estimate the limit of f of x as x goes to 0. Now, if you remember from what we did last time with the tables, we're going to pick small values that get smaller and smaller to get closer to 0. Now, this particular function, we're going to be approaching it from the right side. So we're going to be approaching this from the right side. So let me create a table. So it's going to be x, and then the slope is equal to 2 to the x minus 1 over x. So I'm going to use 1, 0.1, 0.01, 0.001, 0.0001, and 0.00001. And again, we're going to be plugging in into this equation. So the first one is fairly easy. It's just 2 to the 1 minus 1 over 1. 2 to the 1 is just 2, minus 1 is 1, divided by 1, this is going to be 1. The rest of them are going to be a little bit more complicated to do. So I'm going to hop on GeoGebra really quickly so I can show you this. So let's open up GeoGebra. And let me define my function f. In this case, I could call it m. So I have m equals, and what I have is 2 to the x minus 1. And all of this is divided by x. So you can see that this is actually never negative. There's a horizontal asymptote at in the x-axis. There's a hole at x equals 0, because when you plug in 0 here, you get 0 in the denominator. So there's actually not a value here. There's actually an open hole in here. Now what happens when I plug in, what I had before was m of 1. Well, I'm going to get 1, as I clearly and smartly calculated. But what happens when we do 0.1? Well, we get 0.02. And actually, we could change that. Let's see if I could change the view. Instead of 2 decimal places, I'm going to go 5 decimal places so we can see everything better. So this is 0.71773. So that's 0.71773. For the next one, if we go out, m of 0.001, we now get 0.69339. So 0.69339. The next one is going to be 0.001. Oh, that's the one that I just calculated actually. So 0.69339. So 0.01 is the one that I'm missing. So 0.1 is 69556. Or 56. Zero point zero 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 one. So 0.0001. It's 69317. 0.69317. And finally, the last one that I will do is 0.0001, and that's 69315. So as you can see, we're getting the values of x are getting closer and closer to this 693. We began with 1, then 0.717, then 0.695, then 0.693, then again 0.693, and yet again 0.693. So we can say, again as an estimation, that the slope, or the limit, as x goes to 0 from the right side of f of x in this case, is roughly equal to 0.693. So that is, again, an estimation. Now, we have a very nice theorem that will allow us to actually compute these things very, very nicely. It will allow us to get a more precise limit calculation. And that theorem is called the squeeze theorem. And this is a very important theorem. If you're going to be studying mathematics, it's a theorem that you should definitely know and keep in the back of your head, because it's going to be coming up in the future as well. So this is the so-called squeeze theorem. Some people call it the sandwich theorem as well. So if you go to Burger King, for example, you could ask the person at the counter to give you a squeeze theorem burger, and they'll probably look at you perplexed. Okay, so the squeeze theorem will provide us with a useful way of calculating limits. So suppose the functions f and h have the same limit L at a, and assume the function g is trapped between f and h. Well, the squeeze theorem, what it says is the following. The squeeze theorem says that g must also have the limit L at a. So let me just draw you a quick image of what this looks like for the squeeze theorem. So let's say we have three functions. Let's say we have one of them looks like this, and let's say the other one looks like this, and let's say our third function kind of looks like this. So let's give these functions names. My pen will work. So let's say this is f, let's say this is h, and this is g. Then if we're looking for the limit as g goes to 0 right here, and we know that the limit of f and the limit of h are equal, meaning limit x goes to 0 of f equals limit as x goes to 0 of h, and that's 0, then because g is trapped between them and g must pass through here, then g must also have the same limit as both f and h. So the limit x equals 0 of g of x must be the same as h and f. So that's basically what the theorem says. A formal proof of this theorem, if you are interested in reading up on it, you can find it online, proven. I think it's a very nice proof to read. It's very intuitive. So let me actually write the theorem now formally, write it down formally. So theorem. And again, this is the squeeze theorem, or the sandwich theorem, whichever one you prefer. Well, assume the functions f, g, and h satisfy the following inequality. That is, f of x is less than or equal to g of x is less than or equal to h of x for all values of x near a except possibly a. Or at a. Then if the limit as x goes to a of f of x equals the limit as x goes to a of h of x, if those limits are equal, then it must be true that the limit as x goes to a of g of x equals L as well. So then the limit as x goes to a of g of x is also equal to L. Right? So this is the so-called squeeze theorem. So let's do an example of an application of it. Right, so let's use the squeeze theorem. To verify that the limit as x goes to 0 of x squared of 1 over x is actually equal to 0. Alright? So here we have, whoa, hold on. Right now I erased too much. Sorry about that. It is x squared times sine of 1 over x equal to 0. Okay, so here we have to know a few things about trigonometry. So first thing is first. So for any real number, theta, sine is always going to be bounded between -1 and 1. We know this from the sine wave. If you remember from pre-calc, the sine wave looks like this. It's up to 1, down to -1. So, and that's for at any value. Okay. Now, why is this doing this? So let theta equals 1 over x, and remember x cannot be equal to 0 because it's in the denominator. Then it follows that this is also bounded between -1 and 1. Why is this true? Well, again, by definition, we just said that sine is bounded between 1 and -1 for any real number theta. 1 over x, whenever x is not equal to 0, is a real number. You could pick your favorite number for x, it's going to be a real number. You know, it's going to be 1/2, 1/3, so on. So that's always going to be, this is always going to be true. Sine of 1 over x for any real number x except for 0 is always going to be bounded by -1 and 1. Now, before I do the next step in verifying this, I'm going to remind you of something that you should know from college algebra. Let's say we had an inequality like 2 is less than or equal to, let's say 4 is less than or equal to 5. Okay, so we have this inequality. If I multiply this inequality through by any real number that is positive, by, let me not even say real number, by any positive integer, although for any real number it will be fine as well. Let's say I multiply this through by 3. If I multiply 2 by 3, then I also have to multiply the 4 and the 5. So if I multiply through by 3, I'm going to have 3 times 2 is less than or equal to 3 times 4 is less than or equal to 3 times 5. We'll see that 3 times 2 is 6, and that is certainly less than or equal to 12, which is definitely certain to be less than or equal to 15. So if I multiply an inequality by a positive number, I'm not changing the inequality. I'm not changing the statement. The statement still remains true. That is not necessarily the case with a negative number. But with a positive number, we could definitely do that. So note that x squared is always positive. If you remember from pre-calculus, the graph of x squared is a parabola, and no matter what value of x you put in, you always get a positive value. So long as, of course, x is not equal to 0, because if x is equal to 0, then we get 0. So we can multiply all sides of the inequality by x squared, meaning I could multiply all sides of this inequality by x squared. So what will that give me? Well, let me first rewrite it. If I multiply through by x squared, I'm going to have negative 1 times x squared is just negative x squared. X squared times sine of 1 over x is simply x squared sine of 1 over x. And 1 times x squared is simply x squared. And again, since I multiply by a positive number, I have not changed the inequality. Now, this function in the middle is the one that we're interested in. That's the one that we're finding the limit. We're trying to find the limit of as x goes to 0. Now, we can see that this inequality, it's trapped between x squared and negative x squared. And we can also see that the limit as x goes to 0 of x squared is the same thing as the limit as x goes to 0 of negative x squared, which will be 0, because you could just simply plug in and you're going to get 0. So the squeeze theorem says, if we apply the squeeze theorem, says that the limit as x goes to 0 of the function on the inside that's trapped, x squared times sine of 1 over x, must also be equal to 0. That is by the squeeze theorem, which is what we wanted to show. We wanted to verify that this was the case, that the limit as x goes to 0 of x squared times sine of 1 over x equals 0. And that is precisely what we have shown. I'm going to show you, or attempt to show you, how this looks, how these three functions look on GeoGebra, so you could have an idea of what happened here. So let's first get rid of this and this and this. So the first one, I'm going to call it, let's just call it equation 1. And that's going to be equal to x squared. Okay. Now the second one, I'm going to call it equation 2. And that's going to be equal to negative x squared. And finally, the third equation, equation 3, it's the one that we wanted to figure out what the limit was, which is x squared times sine of 1 over x. Okay, so we can see that this function in orange is trapped between x squared and negative x squared. If I zoom in, if I can zoom in a little bit closer, you will certainly be able to see it. And then you will also be able to see what the limit actually is. I can zoom like this, yeah. So notice the closer I'm getting, the more we begin to look like a sine wave, as we should. So if we look very closely here, we can see how the waves are moving, and we can see that the top and bottom of the waves are trapped between x squared and negative x squared as we move closer and closer. So by the squeeze theorem, since the blue line we know that the limit is 0 at 0, and the red line we know that it is 0 at 0, then for the orange line it must be also 0 because it's going between them, or it's attempting to go between them. So if you see, no matter how close I get, they all go through the same value. So this is going to allow us now to work with some very key important limits that are going to be playing a role with trigonometry. There's some very special trigonometric limits that will never go away. No matter how much you try to make them go away, they will always pop up. So these are the so-called trigonometric limits. Okay, so the squeeze theorem is used to evaluate two very important limits. These limits are the following. One of them is the limit as x goes to 0 of sine of x equals 0, and the limit as x goes to 0 of cosine of x, which actually equals 1. Now we will be focusing our attention in the following domain. So this is particularly true when we look at the following inequalities below between the following so I'm looking for between the following range, or rather the word's escaping me now. Intervals. So between the following intervals. So to verify these limits, we will use the following inequalities. Which are both valid between x being strictly bigger than negative pi over 2 and strictly less than pi over 2. So the inequalities that we're going to use to verify this are negative absolute value of x is less than or equal to sine of x, which is less than or equal to the absolute value of x, and 1 minus the absolute value of x is less than or equal to cosine of x, which is less than or equal to 1. So first of all, if we were to graph these, beginning with the sine one, if I was to graph the sine wave between negative pi over 2 and pi over 2, it will look like this, something like that. Well, this is pi right here. This will be pi, it's negative pi over 2, and pi over 2. And the absolute value graph looks like this. So the positive one looks like this, and then the negative one is going to go down like this. So as we can see, the sine wave is definitely trapped between minus absolute value of x and positive absolute value of x. So if we let f of x equals negative absolute value of x, and g of x equals the absolute value of x, and h of x equals sine of x, then we see, actually g I've been calling, let's be consistent, I was calling g the one in question, so this is going to be the upper bound, so the absolute value of x. Then we see that the following is true. G is trapped between f and h on the interval negative pi over 2 to pi over 2, and since the limit as x goes to 0 of f of x is equal to the limit as x goes to 0 of h of x, which equals 0, then by the squeeze theorem, again, g is trapped between these two functions, so by the squeeze theorem, it must be true that the limit of g of x as x goes to 2 is also, as x goes to 0 is also 0. So limit of g of x as x goes to 0 has to be 0 by the squeeze theorem. Now similarly, this is going to be the same case with cosine of x. So to evaluate the limit, as x goes to 0 of cosine of x, then we will use the following inequality, which is 1 minus the absolute value of x less than cosine less than 1. So we have f of x equals 1 minus the absolute value of x, h of x equals 1, and g of x equals cosine of x. So now what we have here, if I attempt to draw it between the interval, let's say this is pi, this is minus pi. So if we attempt to draw it, remember that the cosine wave goes down and then back up. So we have the following. We have goes down, down. So here we have pi over 2, negative pi over 2 at this point, at the intercepts, and then here we have the line of the function. Let me do it in another color. We have 1 over here, so this is going to be h of x equals 1. And then we have the other function, which is the absolute value of 1 minus x. So if you have the absolute value of 1 minus x, it's the same thing if I rewrite it as minus the absolute value of x plus 1, which just means that I'm shifting this up 1 and reflecting it about the x-axis. So it's going to be looking like this. Obviously not to scale, but you can see that the cosine wave is trapped between the blue line and the red line. So again, we can use the squeeze theorem, because on the interval, on this interval, negative pi over 2 to pi over 2, notice that the limit as x goes to 0 of f of x is equal to 1 minus the absolute value of x but since this is a linear function, the absolute value of x is always positive. We're dealing with positive numbers here, so it's just going to be 1 minus 0, which is just 1. So the limit as x goes to 0 of 1 minus x is just 1, and the limit as x goes to 0 of 1, by the rule that I explained earlier in the lesson, is just 1. These two limits are equal by the squeeze theorem. Since limit as x goes to 0 of f of x equals limit as x goes to 0 of h of x equals 1, then it follows that the limit as x goes to 0 of g of x must also be 1. That must be the case by the squeeze theorem. And that is the end of that particular problem. Now, this is going to lead us to evaluating some special trigonometric limits. I'm going to do both of them right now, and then in the future we will see how they are applied. So let's do some examples of this. How understanding this will help us out. So number one will be to evaluate the following limits. So number one, we have the limit as x goes to 0 of sine square x divided by 1 minus cosine of x. So here we have a very particular situation. We have a rational function where the numerator is a trigonometric function and so is the denominator. So we have to recall some more facts from pre-calculus, and one of the facts that we have to recall is the trigonometric identity, the Pythagorean identity for trigonometry. So that's sine squared of x plus cosine squared of x equals 1. Now, how is this going to help us out? Well, I have a sine square on the numerator, and if you didn't know, I can manipulate this. Since I have a sine square here, I could do the opposite operation. Instead of adding cosine square of x, I could subtract cosine square of x on both sides. So this will leave me with sine square of x being equal to 1 minus cosine square of x. And how does that help me? Well, I could now substitute this sine square of x with whatever it is equal to, with 1 minus cosine square of x. So let's actually do that. So we have the limit as x goes to 0, and instead of sine square of x, I'm going to write what it's equal to. So 1 minus cosine square x divided by 1 minus cosine of x. Now, remember that when you have a squared minus b squared, that is the difference of two perfect squares, so that's a plus b times a minus b. You may not realize it, but 1 is a perfect square, because I could write it as 1 square, and I already have cosine as a square, so I could actually rewrite this. So I'm going to do that right now. So it's going to be equal to the limit as x goes to 0 of 1 minus cosine of x times 1 plus cosine of x, all divided by 1 minus cosine of x. Now, so long as 1 minus cosine of x is not equal to 0, I can cancel. I could cancel this 2 out, and I'm left with the limit as x goes to 0 of 1 plus cosine of x. And now I can actually use some of my laws of limits to break this up. In particular, I could use the sum law that allows me to break this up as limit as x goes to 0 of 1 plus limit as x goes to 0 of cosine of x. Now remember that the limit of a constant is just a constant, so I'm just going to get 1 here. And if you plug in 0 for cosine, again going by the cosine wave, begins at 1, so cosine of 0 is going to be 1. And last time I checked, 1 plus 1 equals 2. So we now have that the limit of this problem right here is equal to 2. So if you have somebody in the train, for example, comes in and gives you this problem, they tell you find the limit as x equals to 0 of sine square of x divided by 1 minus cosine of x, you could quickly compute it and tell them that the limit is equal to 2. Finally, the last example for today's lecture is to evaluate the following limit, and that limit is the limit as x goes to 0 of 1 minus cosine of 2x over sine of x. Now for this particular problem, you're expected, since you're in a calculus class, to know what the double angle formula is for trigonometry and the half angle formula as well. So these are formulas that you can derive by using the sum and difference formulas. If you have taken pre-calculus with me, then you definitely will know how to derive these things. If you took it with anybody else, then you should definitely know how to derive them as well, because everybody teaches the same syllabus. Everybody follows the same syllabus. In any case, what I really want you to know is that cosine of 2x is the same thing as cosine square of x minus sine square of x. So that's the identity that we're going to be using here to simplify this. All right? So what do we have? So we have the limit as x goes to 0 of 1 minus, and I'm going to substitute cosine of 2x for what it is equal to, and that is cosine square x minus sine square x divided by sine of x. Now here's the interesting thing. Earlier I wrote a interesting formula, but before we do it, let's see what happens. So we're gonna distribute this negative sign. This thing's not moving. Okay. So we're gonna distribute these negative signs. So I'm gonna have limit as x goes to 0 of 1 minus cosine square x minus sine square x over sine of x. Now this 1 minus cosine square x, remember I had it up here. 1 minus cosine square x, we know from our previous problem, that's the same thing as sine square x. So I could actually substitute again in here. So that's something that I'm going to do right now. So we have limit as x goes to 0 of sine it's actually 2 sine square x over sine of x. You can do the computation and you'll see that this will be the case. I didn't distribute correctly this sign. It's a plus, not a minus. Minus plus minus is plus. So this will be 2 sine square x. And finally, you could, since you have 2 of them, you will cancel out one of the exponents here. So we have that the limit as x goes to 0 of 2 sine x is the same thing as if you were to plug in the 0 in there. But remember, sine of 0 is 0, so this is going to be 2 times 0, which is just 0. So we have that this entire limit that looked very complicated is just going to be equal to 0 once you do the respective operations. So it's going to be equal to 0. Right, that is all I have for today. Thank you for your time.